Well, good morning, grade 12. And I just wanted to say that this is one of my favorite lessons on orbital motion. Like we've been talking about circular motion, centripetal motion, and everything. And actually, there's not really. This is a much sort of quicker lesson and everything. But I would like to talk to you a little bit about the history of all this. We're going to look at Kepler's laws in much more detail than you may have in grade 9. You probably didn't look at them at all if you weren't in my class, but yeah, this guy named Johann Kepler, we've named a this telescope that's floating in space, orbiting Earth. We've named it after him, the Kepler telescope, and actually looks for extraterrestrial planets or extrasolar planets, I should call them. So planets and other star systems, and some of them may or may not support life. We've detected many hundreds of planets. We found the Kepler telescope has told us that there are many planets out there. Okay, so planets are incredibly common. Anyway, long story short about Kepler, though, is he was alive, in the midst of the Renaissance. Okay, and during this time, it's kind of a tumultuous time. Okay, and especially in church history, but also in the history of human civilization. These are some really great people in scientific history were alive at this time. And for physics, the most important ones that we can talk about are guys like Isaac Newton, of course, and we'll get to him. There's Galileo, and he was really important for the scientific method as we know it today. Okay, and then there's Johann Kepler. So Kepler, long story short, he set out to prove that the Earth was the center of the universe because that's what everyone thought. Okay, before Kepler, for thousands of years, really, that was the assumption that they made, just based on the movement of stars and everything, how it looks, right? Anyway, Kepler was a mathematical genius. He figured out how he could approximate distances from Earth to the planets using something called parallax. I don't want to get into it here, but yeah, once you know how far away Earth is from the other planets, you realize very quickly that actually they're not orbiting Earth at all. Okay, and in fact, Earth itself is simply in orbit, like all the other planets are, around the sun. Now, the only thing that we got right in the old model was the moon is orbiting the Earth, and that's actually the truth. Okay. Other than that, all the old model went out the window, and Kepler came up with 3 laws of planetary motion. And this is significant because they're absolutely true today, as they were, hundreds of years ago. In other words, he got it perfect, he got it right, and he did it by measuring it. So these are, we call them empirical laws. When we say laws in the empirical sense, we just mean this is what they're always doing. So this is what planets just always do. In fact, any orbiting body will follow these laws. And yeah, there's nothing wrong with them. He got it perfectly right. And so here you can see there's a sun here in the center of your screen. And what I'm going to do is I'm going to give a planet some velocity. If I don't give it enough velocity, notice it will fall into the sun. Well, that's not good. Okay, that's too slow. Now a little faster, and we get a possible orbit. Okay, now if I go too fast, it will actually escape the sun's gravitational pull. We call that escape velocity. So the escape velocity of this seems to happen right about here somewhere, where then it'll sort of slingshot around the sun and escape the sun's gravity and never come back. Well, we don't want that. So we're talking about planetary motion after all. So let's set this guy in orbit and we'll watch what happens. Okay, so now here we notice 2 of Kepler's laws. The first law is that all planets move in elliptical orbits around the sun. Okay, and so here we see a planet as it gets farther from the sun. Pardon me, it's moving a bit slower now. And then when it gets closer to the sun, it actually speeds up. Now, these green lines that are being drawn from the sun, to the planet are called radial lines. And one of Kepler's laws was that a radial line will sweep out equal areas in equal time intervals. So let's pretend that each one of these little segments you're seeing here represents, I don't know, a week or something, okay? So then what happens is as the planet moves from one green line to the next, one radial line to the next, a week has passed. So you see a week when the planet is at its perihelion, like it's approaching its perihelion when it's moving the fastest, right there. Peri means close. So perihelion means close to the sun. Its aphelion is quite far away. That's when it's at its farthest distance from the sun. It's just approaching it right now. So right about here, it's at its aphelion, okay? And then it's moving quite slow at the aphelion, covering a lot less, section of its orbital track compared to when it's at its perihelion, when it's moving very quickly, okay? Now I'm going to clear this one, and I want to show you that, let me pause that, and let me reset it. Okay, so look, if I drag these velocity vectors around, oh, that was going to fall into the sun. Oh, end of life. There you go. Let me reset that again. Okay, I want to see if I can get something that resembles a circle. I gotta get it. Gotta get that sun in the middle, right about there. So a circle is actually also an ellipse. So if there's no difference between the peri and the aphelion, we say the circle has a very, like an eccentricity of 0, okay? So a circle is an example of an ellipse with an eccentricity of 0. The lunar orbit around the Earth is approximately this shape, and Earth's orbit around the sun is also approximately this shape with an extremely low eccentricity value. Comets, on the other hand, have very high eccentricities. So let me reset this. Comets have extremely high eccentricities where they get really close. Let's see if I can get really close. Oops, let me reset that. I drew a second one there by mistake. Let's see if I can get it really close and then get the aphelion really far. So there, my perihelion is really close here. All right, let's try that. So now it's going to really whip around there. This is what comets do. Okay, so comets spend actually very little time in the inner solar system. Then they go way, way out past Pluto. Okay, in some cases even farther than that. Okay, and they can have very, very slow rates of movement when they're at their aphelion. So like right now, Halley's Comet is somewhere close to its aphelion. And it's about to come back towards the inner solar system. We'll see it again at about 2060 or something like that. And hopefully we'll all be around to see it, right? Halley's Comet. You should be. I mean, I'm doing all right. I think I might be around at that time. I've already seen a really impressive comet though, Hale-Bopp. You weren't there because you weren't born yet. And that was very impressive in the late 1990s. Okay, so I'm going to pause this. So there you go. There's 2 of Kepler's laws. The third law is a mathematical law. There's a connection between the radius of orbit and the period, which means the time it takes for one lap. And that's Kepler's third law. So now that you've seen this little demonstration, let's go to our notes. Everyone's favorite. And there's the handsome gentleman, Johann Kepler. Okay. Wow, these beards, they've got to make a comeback at some point, right? So I told Dominique, my wife, I said, I showed her this picture and I said, you know what? I think that I should, have this Tycho Brahe beard here and the mustache. She goes, no. So, you think you're in charge of your own life, but, I can't complain, honestly. I'm doing all right. But I can't have this beard as much as I would like to. I do have Isaac Newton's hair though, so I'll go with that. Okay, so she lets that go. All right, here's Tycho Brahe. Now, here's the deal. Him, like here he is with his mentor. Okay, Johann Kepler and Tycho Brahe. And Tycho Brahe was more of an inventor, less of a mathematical genius, and he invented this thing called the sextant. This is a very large one, and this is used to make very precise angular measurements of altitude. Okay, so like if you go out at night and you measure very precisely the distance from the horizon to a planet Venus, let's say. In fact, in about 2 weeks, 2 or 3 weeks, Jupiter and Saturn are going to appear as a double planet. They're actually really close to alignment right now. And that only happens like once every 800 years or so. So you should feel special about that. Okay. Anyway, Tycho Brahe invented the sextant, and that's how he was able, long story short, to measure the distances to the planets using a little bit of trigonometry in this thing we call parallax. Okay. He had a lot of help. It took him years to do it, but he was very good at collecting data. Okay. All right, so let's do the laws one at a time. Law number one, planets move in the elliptical orbit with the sun at one focus. So let's see if this little demonstration will show up here. Okay, so there's a planet going around the sun. This is a kind of crappy animation, but whatever. An ellipse is like a curve with two focal points. One focal point for a planet's orbit always has the sun present. The other focal point has nothing, okay? And that is characteristic shape of an orbit. But a circle is also an example of an ellipse, except the two focal points are at the same spot, okay? And that's what makes you a circle. You have a very low eccentricity with the two focal points at the same spot. So that's law number one. Planets move in elliptical orbits with the sun at one focus. Law number two, okay? Law number two is that planets will sweep out equal areas in equal time intervals. So for example, this is an exaggeration. Forget day, let's say it's a month. So that's a month from A to B. And then what happens is when it's closer to the sun, it moves faster. So when the radial arm is short, it speeds up. Okay. Now, later this would become something that was called, Newton called the law of conservation of angular momentum. We don't do angular momentum in high school. It's a university thing. But you know when a figure skater pulls in her arms and she spins faster, same thing is happening to planets when they get closer to the sun, especially comets with that highly eccentric orbit. Now, basically, I summarized it for you here. I'm sorry, my drawing is awful, but I apologize for that. But it goes like this. If this area here, this yellow area here is the same as this red area here, if the planet, they'll be the same if the planet here moves across this arc here in the same amount of time that the planet will move across the arc close to the sun. So what happens is in order for that to happen when it's at its perihelion, it has to be moving faster, okay? So that's the deal. All right, now the third law is kind of interesting. If you take the mean radius of orbit, okay? So like, you know, if I were to draw an orbit for you here, like this, here's the sun here, let's make it red. It's like Superman's sun, like my home planet, guys. I come from a world with a red sun, okay? So if that's it, then the mean radius, R, is just an average value. It's the distance between the sun and the planet. And you know, you would average it out across the entire ellipse, so you can have a smaller R value here. But that's what R represents, the distance between the planet and the sun, okay? Now, T is the time it takes for one lap. Now, since you live on the Earth, you know how much time it takes for the Earth to orbit the sun once. We celebrate your birthday every time it does it once, right? It's a year, okay? So you were born when the Earth was at a certain spot. Okay, if you're born in December, the Earth is like almost at its perihelion then. Okay, so if you're born in December, like Earth's over here somewhere, right? And every time the Earth is over there, we say happy birthday to you because your birthday was in December, okay? My birthday's coming up, so, you know, I do accept gifts from my students, and, you know, you want me to give you a good recommendation, right, for your university program. So anyway, I am in the market for, like, you know, more Teslas and stuff if you wanted to chip in. But here's the deal. Something that's unusual, every planet has its own R and its own T. Like, so for example, Mercury goes around every couple of months. I mean, we're going to measure time in Earth context, right? So Mercury only takes a few months to go around the sun, whereas Earth takes 12 months, right? 365 days. Jupiter takes like 11 years to orbit the sun once, so it's going very slowly, right? Saturn is even longer than that. So the deal is, the farther you are from the sun, the longer your year is. Okay, that makes sense. And also, of course, the bigger your radius is, but radius of orbit. But Kepler noticed a mathematical pattern. He noticed that if you take the cube of the radius and divide by the square of the period, you end up with a constant that we call Kepler's constant. And the constant is actually written, let me use a rainbow because it's so special. This is Kepler's constant for our solar system, 3.36 times 10 to the 18 meter cubed per second squared. Now Kepler sees this number. What does it mean, right? What does that mean? Well, it doesn't mean anything, right? It's kind of weird that it's a constant though, because there's something special about that number. Well, yeah, it turns out that there is, but for Kepler, it really had no meaning. Remember that these laws, he's just saying what the planets are doing, okay? So for whatever reason, they do this. And he just recorded the value. See, that's an empirical law. You can't argue with data. So these are simply facts, statements of facts. This is what not students, but what planets do all the time. Maybe students do it too, I don't know. I guarantee that if you chose to orbit the sun, you would obey these laws also, okay, in your little spacesuit. All right, so here's the deal. Actually, we don't yet care about the mass, so you can ignore the mass for the moment. But here's a survey of our solar system. You'll notice that Venus has a radius of orbit. Now, here, you got to be careful here, okay? Let's go with Mercury. Let's go with the first item in the table. So what we mean by radius of orbit is the distance to the sun. This is the radius of the object itself. Remember, all the planets are basically spheres. So don't confuse this. This is the object itself. This is the planet radius. And this is the orbital radius here. Okay, so that's the radius of orbit. And this is the period of revolution, is t, how many seconds it takes for the planet to go once around the sun. Okay. Now notice there's a pattern of increasing values as you go down, okay, for both the, the period and the mean distance, okay, the R value. Okay, but there is actually a pattern in these numbers. Now we don't want to count the moon and the sun, okay? Let's cross those out because they're not orbiting the sun. All right, so now let's take a look at some of these values. And like, for example, if I were to take like the highlighted value for Mercury here, so this number here, 5.79 times 10 to the 10, okay, and this is the period, and go R cubed over T squared. I'll use my calculator, so I go 5.79 times 10 to the power of 10. I'm going to cube that number, and I'm going to divide it by 7.6 times 10 to the power of 6. And I'm going to square that number, and I press equals, and I get 3.36 times 10 to the 18. Now, do it for, let's erase this one. If you do it for Venus, you would use Venus's radius of orbit and Venus's period of revolution. And trust me when I say here, I'll put the numbers in just to satisfy your curiosity, because I know you care. So it's 1.08 times 10 to the 11. I'm going to cube that number, and I'm going to divide it by 1.94 times 10 to the 7 times 7. I'm going to square that number, and I get, 3.35 times 10 to the 18. A little off, but close enough. And then when you get to Earth, Earth is obviously another planet. Look, you just get the same number, like a broken record. In fact, it could be a golf ball orbiting the sun. You would still get this number, okay? If it could be closer to Mercury, it could be as far as Halley's Comet. It really doesn't matter. You always get this number. Okay, now, and Kepler had no idea why you get that number. Okay, so there you have Kepler's 3 laws of motion. Okay, and this year, unlike grade 9, I would expect you to have these laws memorized. Okay, so we're talking about orbital motion, and so Kepler's 3rd law is actually really important, and that's it. All right, now let's move on to Isaac Newton. So let me go to orbital motion in terms of Isaac Newton. I'm sorry, wow, we zoomed way out. Okay. Oh gosh, I forgot. When I first made the note, I put a student's face on Isaac Newton's body there. That's hilarious. That is Quinn Ariel. That's who that is. That's Quinn Ariel. It's so funny. That's from a couple of years ago. Oh well, I'll put your face in there at some point. Let's pretend that's Isaac Newton there. Actually, wait, can I move that? No, I can't move it. All right, so anyway, guys, look, is this why he is a genius? I mean Isaac Newton, not this guy. And see, my hair is kind of like that. That's fake hair though. They used to wear wigs back then. But Isaac Newton actually, when he was younger, had long hair. Not as nice as mine, but you know, he had long hair. Now, a apple hits the head, falls on a tree. Hey, look, it's gravity. Is that why he was a genius? Not really, actually. The genius of Isaac Newton was more to it than that. Okay, and I'll explain what his genius was in a second here. But here, just take a look at this cartoon. Okay, so it says, why have you stayed with me all these years? Well, I'm locked into your gravitational pull. Oh, I love you too. Isn't that nice? I mean, we are actually physically attracted to each other. Now, what I mean by that, nothing weird. It's a YouTube video, nothing weird. I mean, the force of gravity. But I gotta say, the gravitational attraction between us is incredibly weak. Okay, so don't worry about it. It's nothing weird. Okay, think of it as like this universal force at work. You're not actually repulsed by anyone, you're only attracted to them by the force of gravity. Now, of course, how you feel about that could be attractive or repulsive. That's up to you, okay? But what we mean by the force of gravity is that every mass in the universe attracts all other mass in the universe, and this is the force of universal gravitation. And the real genius of Newton, the real genius, was not understanding that, like, you know, this apple, say, for example, falls to the ground, and just giving it a name, well, let's call that force of attraction gravity. No, it was connecting that to the reason why planets orbit the sun. So planets used to be considered celestial beings, like the Greek word for Jupiter is Zeus. Zeus is the Roman word, or Jupiter is the Roman word, but the Greek one is Zeus. Well, it's a god of lightning and thunder, you know, like the king of the gods or whatever. But yeah, you know, why do the planets have these names? Well, they thought that was the realm of spiritual beings out there in the heavens. And what Newton realized that no, actually, that there wasn't like these two realms, the heavens and the earth. There was just one universe with all the same physical laws at work. And that's what we've been studying, right? Is Newton's laws. So this is now the fourth law, okay? So let's just take a look at how Newton understands gravity. Okay, and like I said, his eureka moment, his thing he's most famous for was connecting gravity here on Earth, which is what makes apples fall, to gravity in the universe, which makes orbits happen, like the Earth orbiting the sun. Okay, so here's the deal. Gravity near the Earth, we know very well it is our good friend. Gravity gives you exercise every day as you fight against it. Okay, so we just go the force of gravity equals mg. This is equal to your weight, of course. M is your mass in kilograms, and g is 9.8 meters per second squared down. And that works basically everywhere you can stand on Earth's surface, from the top of Mount Everest down to the depths of Death Valley in California, right? Like, so whether you're at very high altitude or very low altitude, it doesn't really matter. It's around 9.8. But if you're going to get 100 kilometers away from Earth's surface, well, now you're going to get some drop in that acceleration due to gravity, and we need something else. So in the entire universe, this is everywhere, including Earth, including right where you're standing right now. Okay, we don't have one rule for where you're standing right now. This just happens to work, but this works too. Okay, this actually works everywhere. So that's what we mean by universal. It works everywhere. We know that the force of gravity is actually directly proportional to the two masses that are attracting each other, the product of those two masses, but it's inversely proportional to the distance between those masses. And if we put all of that together, we get Newton's universal law of gravitation, which is this formula right here. I'm going to highlight it in yellow. And I'll also put a rainbow around it because it's pretty. Okay, so here is your universal force of gravitation. We did this in grade 11, like we touched on it once, you know. But anyway, the universal force of gravity between two objects would be a constant, big G, times the product of the two masses divided by the square of the distance between them. And this is how big that constant is. It's actually a really tiny number, okay? A really tiny number, like 6.67 times 10 to the negative 11. Now, here's the deal. You have two objects. We measure distances between them, is distances between r equals distance. Whoops, not distance, but distance. Okay, distance center to center. So what's the distance between you and Earth right now? It's not 0 because you're standing on it. It's the distance between you and the center of the Earth, which is around 6,400 kilometers, okay? All right, now, remember Kepler's third law. Well, Newton has something to say about this. And see, now that you've done circular motion, you have something to say about it too. Okay, so let's go through how Newton figured out what Kepler's third law is really all about. Okay, so let's take a look at that right now. First, we'll start with a free body diagram of a planet going around the sun. What else will we start with? I mean, it's Newton's law. So here's our sunshine, color it yellow. There's the sun. Now the sun has a certain mass. Okay, that is called ms. Earth also has a mass. Let's call it mp, mass of planet. Okay, now when Earth is going around in its approximately circular orbit around the sun, there's really only one force at work. Now, yes, it's moving this way. This is a property of circular motion, right? But it's got radial acceleration towards the sun all the time, okay? Now, you see how Newton put it together, right? If there's acceleration, there must be a force. And what is that force? Well, he realized it was the same one that caused the apple to fall from the tree. So it is this same thing, okay? Gravity. Okay, gravity is causing the radial acceleration, and there's no other force out there making the planet move. Remember Newton's other laws. An object in motion tends to stay in motion. Its inertia makes it keep moving. Okay, and Newton said that what made it initially move, so how come the Earth has just the right speed to stay in orbit around the sun? Because Newton knew if it went too fast, it would escape the sun and we would all die. If it went too slow, it would fall into the sun and we would all die. It has just the right velocity. And you know Newton's explanation for that, why planets had all just the right velocities? Because God did it, okay? Because God gave the planets. He called God the prime mover, which means like he set everything into this perfect motion, and then the universe has basically been working like clockwork ever since, okay? So anyway, that was his explanation. All right, now here's the deal. We know how to break down circular motion. You guys are pros at this now because you know you've been working hard, right? So start with that. The radial acceleration equals v squared over r. Now the deal is we're going to look at the net force. There's only the force of gravity acting on the object. Okay, so that's the only force. And therefore what we get is mp, we'll call that mp here, mass of planet. Okay, mp/ar, so this is the net force, is equal to just the force of gravity, and this is Newton's formula for universal gravitation, right? And now let's see if we can simplify this, okay, and we solve it for v. And so this is, you know, what we do is the mass of the planet, oh, I'm sorry, it's a silly thing. The mass of the planet here cancels out, not the mass of the sun though, because we drew a free body diagram of the planet, right? The one that's doing the orbiting, the one that's moving in the circle, okay? So that's why it has centripetal or radial acceleration. So it's that mass cancels. One of our r's will cancel with the r in the universal gravitation. Remember how we substitute ar as v squared over r? So one of the r's cancels out there. Okay, now here's the deal. We're going to do this time. We're going to use that speed equals distance over time. So v is equal to 2 pi r over t, right? Circumference divided by period. And period is the time for Earth, like the 365 days. Okay, that's the period. Now, if I substitute that in for speed in the centripetal motion, like in the force equation here, see how speed is squared? So I have to square that whole thing. So when I square 2 pi r over t, I get this. I get 4 pi r squared over t squared on this side. And then I have big G times the mass of the sun divided by r on that side. Well, I'm gonna cross multiply my r, okay, and I'm gonna put the 4 pi squared on the other side. Now, the reason why I'm doing that is because this looks like the left-hand side of Kepler's third law, r cubed over t squared, right? But you see why it's a constant. See, Newton had a better sort of was able to explain this better than Kepler. He still couldn't tell you why gravity is happening, but he knows why you get a constant. Anything that orbits the sun, this will be true. And if you look at this, these are all constants. Big G is that 6.67 times 10 to the negative 11. But look at ms, that's the mass of the sun. Okay, so anything that orbits the mass of the sun, you're gonna get this to work out. Like we never put in any specific values. So it could be a golf ball orbiting the sun. It doesn't have to be a planet even. And this will still occur. And then 4 and pi are also constants. See, and so this is Newton's version. This is Kepler's constant here. We know that Kepler's constant, it was determined empirically to be 3.36. Pardon me. 3.36 times 10 to the 18 meter cubed per second squared. Well, you see, because we know these other values, guess what? We can find the mass of the sun. See, and that's what you can do. That's the amazing thing about Newton's contribution here is all of a sudden these guys that didn't even have telescopes, right? Well, Newton did. Okay, by the time Newton was around, they had some pretty nice telescopes. In fact, Newton invented some of the optical systems that would later become the telescopes we have today. But here's the deal. Let's now combine what we know about Kepler's empirical law, so 3.36 times 10 to the 18, and solve it for the mass of the sun. And when you do that, you find that the mass of the sun is this huge number. Now, for reference, the mass of Earth, you can also figure out, okay, using Newton's law of gravitation. You know how you work out the mass of the Earth? I should show you this. Okay, here's the deal with the mass of the Earth. Let's say we draw a free body diagram. You drop a ball, and while the ball is falling, you draw its free body diagram. A ball falling. Here's the beautiful thing about this. Okay, so watch. Here's a ball falling. There's only one force, gravity, right? And of course it accelerates down. And it's radial. Well, it's not radial, I shouldn't say that. It's not orbiting. So it's just acceleration due to gravity. 9.8 meters per second squared, right? Broken record, you know this already. However, okay, when you look at the planet, so here's the planet, here's your little falling ball up here. So this distance between you and the center of Earth we'll call r, between your ball and the center of Earth. Well, we know this number is 6.4 times 10 to the 6 meters, okay? So now we're going to go like this. MA has to equal big G M, we'll call this MP, this is the mass of the planet, times the mass of the ball. Okay, oops, this is the ball this time. Pardon me. Gosh, I'm getting tired. Okay, so the mass of the ball times A. Remember, this is the free body diagram of the ball. So it's the ball's mass that cancels out. Now this is divided by r squared. Solve it for the mass of the planet. Mass of the planet will equal r squared times A, okay, divided by big G. Okay, just cross multiplying, right? Will get you there. And when you get that, just take 6.4 times 10 to the 6. A is 9.8, so 6.4 exponent 6 times 9.8 equals this, 6.4 exponent 6 squared, pardon me, times 9.8 divided by 6.67 exponent 11 negative equals, and I get 6.0 times 10 to the 24 kilograms, and that's Earth's mass. Now, if you look at the sun's mass by comparison, I put 5.99. Earth is getting a little bigger. It's been lifting weights. So anyway, you see how many powers of 10 there are difference here? Like that is 6 powers of 10. 6 powers of 10 make a million, but it's only about half a million because we have Earth is 5.99 and the sun is 1.99. So that's about 500,000 times, or about a third of a million, 300,000 times, more massive. The sun is 300,000 times more massive. So anyway, there you go. Now, what we've done is we've done all the basic things that you need to solve an orbital problem. So let me go over to the worksheet I put here, and this is our last worksheet in this unit. So here's a worksheet. It has several questions in it. I believe I have answers for you somewhere. I haven't posted them yet. Maybe they're not here. Is there answers anywhere here? Yes, there are answers at the end. So take note of the answers there. Okay, now let's take a look at this worksheet. Notice it says Kepler's laws and universal gravity worksheet. So here, what is the force of attraction between a 60 kilogram student and the school? So are you attracted to your school? Well, you kind of are. Okay, we can prove it. Okay, let's say you're 100 meters from the center of mass of the school, and the school is 65 million kilograms, 65 million kilograms. So 65,000 metric tons. Yeah, maybe. It's a big school, but yeah, building, okay, size. And you're this paltry 60 kilograms. Anyway, work it out. You're attracted to the school. Get over it. It's the truth. Okay. To do that, all you have to do is use the formula. You don't really need a free body diagram. It's too simple. So the force of gravity is big G. In fact, you don't really need a free body diagram for any of these questions. Just go ahead and use the formula. Okay. You do need some data sometimes. So notice the data at the top. So we'll go with that. All right then. If it's an unknown planet, okay, be careful there. Okay, not to use 9.8 or anything like that. Okay, so I'll let you do this. These proportionality questions, I think you can handle it, to be honest with you. It's just using a formula. So just use the formula all the time. Now, by the way, you can use Kepler's formulation of this. So this is Kepler's formula, like I call it the Newton-Kepler formulation. So keep this formula in mind. Here, I'll write it over here for you. R cubed over T squared equals G, mass of the sun, usually the thing that's in the center, divided by 4 pi squared. Now this is ms, is the mass of the object being orbited. Okay, so that's the mass of object at center of orbit. You can use this. It saves you some time and energy. Okay, so like for example, okay, so here, question 8, it says the space shuttle is traveling at this speed while in orbit. How far away is the surface of the Earth? No, that's not a good example of that. Yeah, okay, so here's a good one, number 10. It says a geosynchronous orbit is one where the satellite orbits the Earth with the same period of motion as the Earth on its own axis, which is a 24-hour cycle. Okay, how far from the center of the Earth is a satellite's orbit? So here you can use r cubed over t squared equals g times mass of Earth divided by 4 pi squared. So here you can use that. And that'll save you some time. Okay, I like using that little Kepler Newtonian derivation of the equation. And it's just a combination of universal gravitation and Kepler's third law. All right, that's it for me. So guys, I hope you enjoyed it. Satellite motion. Please do the worksheet, okay? Practice the questions here. And I'm not sure we'll have a quiz on this or not. We will definitely do the circular motion quiz this week though. And I will see you soon.